Good evening, my name is Guy Edward and I'm a member of Group 4 Final Year Project. Our project is Graph Reasoning Generative AI for precision screening and management of antimicrobial-resistant urinary tract infections. The next slide, I'm going to talk about the background and introduction. And under this, I'm going to talk about our keywords. And our first keyword is urinary tract infections. UTIs are usually bacterial infections that affect the urinary tract of a human being. Our next keyword is antimicrobial resistance, and this is a condition where bacteria or other microorganisms evolve and become resistant to medications or antibiotics, where when such a medication is applied to them, it can no longer affect them. The next keyword is graph reasoning. Graph reasoning refers to the process of developing relationship between two different entities, and in our case, we achieve it using a graph neural network where we construct a knowledge graph and then a relationship established between different patients or their demographics. Our next keyword is generative AI, and generative AIs, one of the examples are GPTs, and these are types of large language models which help to give reasoning and information to the user or the client based on what type of information they have been trained on. Our next keyword is a dictator twin, which is a virtualization of a system, and in our case scenario, a dictator twin is a virtualization of a patient which is a dictator patient, and this mirrors the characteristics of an actual patient. For example, the demographics of that patient, including the genes of that patient. The other keyword is precision medicine, and this is a term that is used to refer to tailoring medication according to specific characteristics of an individual. These include but not limited to their genomics, to their gender, or their race, for example. Next slide, I'm going to talk about the literature review, and this has the papers that we reviewed. That one of the papers is graph neural networks for clinical risk prediction based on electronic health records. And the reason we reviewed this paper because it has graph neural networks and electronic health records, which are exactly some of the things that we are using in our project. The next paper is AMR-GNN, multi-representation graph neural networks for resistance prediction, and this paper has AMR-GNN and genomic representations, which are part of the things that we use in our project. The next paper is medical dictator twins for precision medicine and decision support. This paper has dictator twins and precision medicine, which are among the things that we use for our project. And then the other paper is trans-AMR, an interpretable transformer model for accurate prediction of antimicrobial resistance using antibiotic administration, and this paper was chosen for the same reasons. Next, I'm going to talk about the problem statement. I'm going to start by talking about the domain application problem, and the first problem is the rising antimicrobial resistance, and this is a problem because the normal antibiotics that exist are no longer being able to treat the urinary tract infections that exist, and for this case the UTIs keep rising. The next problem is lack of patient-specific treatment strategies, because of most of the clinical decision making depend on an abstract of the patient's characteristics or the patient sample space. There's lack of patient-specific treatment strategies. Next, I'm going to talk about the computational problem, And one of the problem is modeling complex relationships that exist between patients, pathogens, and treatment, and capturing the interaction between multimodal data. This involves data, for example, for our case, to be the different types of antibiotics that are being used to treat the patients. The other problem is simulating patient-specific disease progression and treatment outcomes in real time. This is because we need to develop a dictator twin that should be able to simulate the progression of the patient in real time. The other problem is synthesizing clinical knowledge and reasoning over patient and treatment data. First question is, how can heterogeneous biomedical data be effectively integrated to support personalized UTI treatment? And the solution is that to develop a graph-based model that integrates genomic and microbial data to actuate patient representation. And the next question is, how can generative AI, e.g. GPT models, be leveraged to generate interpretable and clinically actionable recommendations for UTI treatment while considering resistance profiles? And then our objective is to integrate a generative AI model to produce interpretable and context-aware therapeutic recommendations for UTIs, aligning predictions with AMR patterns and clinical guidance. Then the other question is, how can dictator twin simulations improve evaluation of drug host pathogen interactions in personalized UTI treatment? And then the objective is to design a dictator twin to simulate patient-specific responses and optimize treatment. And then the other question is, what is the effectiveness of combining graph reasoning, dictator twins, generative AI in reducing empirical antibiotic use and providing treatment precision in UTIs? And then the objective is to evaluate the performance and clinical impact of an integrated AI system that combines graph reasoning, dictator twins, and generative AI for precision UTI management. The next slide is the research contributions and outputs. Our first contribution is that we developed a graph-based model that integrates clinical records, patient genomics, microbial data to accurately capture each patient's infection characteristics. And then next we applied semantic reasoning within the graph model to resolve the semantic mix across datasets, enabling consistent interpretation of equivalent concepts such as resistance genes and antibiotic susceptibility. We built a patient-specific dictator twin that simulates PD-informed drug responses and pathogen interactions. We developed an AI-driven model that combines graph reasoning, semantic reasoning, and dictator twin simulations to generate interpretable patient-specific treatment such that we achieve the precision medicine bit of our project. Then next is our methodology and architecture. Our architecture is divided into 5 layers, and our first layer is the data acquisition layer, where data is preprocessed, and then it's passed into the next layer, which is the feature engineering layer. And in this layer we have the deep autoencoder that is responsible for reducing the noise in the data and also handling nonlinear relationship before the data is passed on to the inference layer. And the inference layer has the cross-model attention network that is used to handle multiple predictions of antibiotics simultaneously. And then we shall have the generative reasoning layer, and this is the layer where the predictions that are got from the inference layer are turned into natural language, such as recommendations, such as prescriptions that a human being can understand. And then our last layer is the dictator twin layer, and of which this is the layer where precision medicine is provided to a specific patient according to their specific attributes. sorry. Next, we shall have the dataset description. Our dataset name is AMR UTI, antimicrobial resistance in urinary tract infections, and the source of the dataset is PhysioNet. Institutions include Massachusetts General Hospital, and the collection of the data was carried out between 2007 to 2016, and the total specimen in the data include the total specimen were 116,902, and then we have 4 antibiotics, the dataset. And then the dataset also contains 4 files that we will use to carry out our project. Next, I'm going to talk about the exploratory data analysis, and this is the EDA that was carried out on the dataset. These are the different visualizations, where the first visualizations characterizes the patients under white versus non-white, and then veteran versus non-veteran. The next graph on the top shows the top 10 important features in our dataset, and then below we have the graph that shows the prescription versus the NIT resistant outcomes. The next graph is the distribution of the patients that were sampled or that are in our dataset. Next are other visualizations of the data, and then the 2 visualizations up are the PCA visualization of clinical features. The first one is the 2D, and then the third one is the 3D visualizations of the data. Below we have the co-resistance correlation heat map that is between antibiotics, and then we have the average resistance rate per antibiotic. Here I'm going to talk about the models and their evaluations plus the results. First, the results of data pre-processing, of which in our dataset we have 0 missing values, and we have 790 numeric features, categorical features 1 and 4 targets, and the 4 targets are the antibiotics that were used. Below we have visualizations, one of the antimicrobial resistance label distribution and the processing output, and then the other of the correlation between resistance labels. Next, we have on layer 2 of our methodology, we have the autoencoder and the evaluations. The variations of the base loss of the encoder is shown 0.010074. Then we trained 100 epochs on this. Then the runtime was 196.93 seconds. Trained it on a CPU, and below it is the autoencoder training loss curve, and then aside of that there's the reconstruction error distribution of the autoencoder. Then on my next slide, we have from the inference layer we have the cross-model attention network MTL test metric summary, and this was our first supervised learning model, of which shows the following results displayed on the screen. It has the accuracy of 58 for the NIT antibiotic. For the XX antibiotic we have accuracy of 67.90, and for the CIP antibiotic we have accuracy of 82.30, and for LVX we have accuracy of 82.20, plus other metrics that were evaluated as shown on the slide. Below we have the training versus validation loss of this model. Thank you for listening to this video.